interval and difference between two proportions. Now I'm going to do the first one, the first example. I'm going to do it by hand, well, mostly by hand. And then I'm going to show you a really cool feature in the TI-84 that essentially does everything for you. You just put in the information. So that will save you a lot of time. So let's have a story. Let's have a story so we can look at this type of question where you need to find a confidence interval on the difference between two things. What you're going to have is two samples. So since we're in the medical field, we'll have on one the old medication, and on the other side the new medication. And you have some people with an illness, and let's suppose you take a sample of 200 people with the illness who receive the old drug, and 100 people who receive the new drug. So we have a coding system. We'll call this 1, we'll call this 2. So this will be called N1 and this will be called N2. So that makes sense. So, you know, if I say N2, you know which one I'm talking about. If I say N1, you know which one I'm talking about. Now, let's suppose the people who took the old drug, 150 of them got better, right? I guess the opposite of that is the other 50 died, right? But whatever. Right, 150 got better. So we'll call that X1. And the proportion who got better is 150 out of 200, which is 75. So you would say that the old drug had, what, a 75% success rate, right? What about the new drug? Well, 80 of them got better. Now, when I look at that superficially, and this is done quite a lot, you know, when they have a new procedure or a new drug and they want to test it, and they have to compare it against something else, right? So typically they test it against what the old drug is, right? What's the one that we use right now to treat heart, you know, fibrillations? What's the drug we use right now to do reduce blood pressure? Whatever it is, right? So you got the old drug, and then you got this new pill, and they're saying, oh, this one's much better, right? It does a better job, whatever that means, and you want to compare them. So the way that you do it is you compare the difference between them. Now, it's just on the raw data. It does look like the new drug is more successful, right, than the old drug, right? 80% success rate on the new drug, 75% on the old drug. But you can't really just make your decision based on this. I mean, you can't suddenly say to all the doctors in America, stop using the old drug, start using the new one. And we'll forget about all the other things like side effects, right? We'll assume that they're equal, right? Because couldn't that just be a little bit of luck? Couldn't actually the new drug and the old drug be pretty much equivalent? Right, same success rate. You just got a few extra people here, or you got a little bit unfortunate with your group here. So what we need to do is we need to find what the difference between them is and then put a confidence interval in it, and we can use that to come up with our judgment call. So we now need to put this together. And we're going to have to calculate a single number, the standard error, right, the estimate version. Now, can you remember yesterday that was the square root of p hat 1 minus p hat over n, right? But now we have to do it in such a way that we use two separate sets of data and combine them into a single standard error. The formula is a little bit ugly, but this is what it looks like. P1 hat, 1 minus P1 hat over N1. That looks very familiar, doesn't it? Now here's the extra bit. Plus P2 hat, 1 minus P2 hat over N2. Kind of makes sense as a formula, doesn't it? You're just like adding the two standard errors inside the square root. So it's not that you're finding this standard error plus this standard error and adding it. It's a little bit messier than that. Have you noticed that the two things belong inside the same square root? It's not one square root plus a second separate square root, right? It's one big square root where the formulas are inside. Now that is really messy. And here goes. For group 1, it's going to be a 0.75 followed by a 0.25 divided by 200. And then it's going to be a 0.8 times a 0.2 all divided by 100. So far, so good? Right, now, where is it? Calculator time. Now, this is the long way. I haven't shown you the shortcut way, right? This is going to be the long way. But essentially, I have to take all of those calculations and figure out what that standard error is. So here goes. I know, can you see what I'm typing here? It's a little bit small. I don't know what I can do to make it better. It's hard to do. Maybe I'll put a light on. Aye. Maybe better. I'll go for it. So it's going to be the square root of 0.75 times 0.25 divided by 200 plus 0.8 times 0.2 divided by 100, and the answer is 0.050 to 3 decimal places.
The light makes it worse.
Okay, so I won't use the light again then. Right, but can you imagine you typed it in and that's what you got, right? So we're about 3/4 of the way through right now. Our goal is to get a confidence interval for the difference between these two, and then at the end we'll interpret what does that tell us or what does it not tell us. Now here's your formula. Well, which one do you want, 90, 95 or 99? Pick one.
95.
Okay, so we're going to do a 95% confidence interval. The formula is P1 hat take away P2 hat because it's the difference that we want, right, between the two. Right. Plus or minus that funny little guy there times the standard error. Okay, let's see what's the same, what's different kind of thing, right? Do you agree that this here is very similar, right? This weird guy, Z star 0.95, do you know that's a placeholder for a number? And there's only 3 numbers you ever use in any kind of confidence interval, right? Do you remember which one is the 0.95 one?
1.96.
That's the one. So it's going to be plus or minus 1.96. The standard error is 0.050. P1 was nothing 0.75 and P2 hat was 0.8. Are you all happy about where all those various bits and pieces are coming from?
Yes.
You all happy where that, take away that, that's P1 take away 2, the magic number for 95% and the standard error estimate that we calculated a few moments ago. Now, you take this away from this and you get a negative number. Now I'm going to do the next bit. I'll just type it in. You don't need to see it. 1.96 times 0.05, and I get plus or minus 0.098. Okay. So far, so good?
Yeah.
Okay, so what would that look like? Well, you take this and you add it. I guess normally you wouldn't need to write this down. You're going to take it away. So you wouldn't normally do that. You would just do it in your calculator, but I'm writing it down so you can see where it came from. So, oh, the little issue. When you're doing the calculator and the first number is negative as it is here, you remember to hit this negative button and not the subtraction button, because it will just say error if you do the subtraction button. So negative 0.05, now you can subtract 0.098. And the answer I get is negative 0.148. And then if you do the other side, negative 0.05, and you add 0.98 on the other side, you get, try that again, I know it's wrong, negative 0.05, that's better, plus 0.098. And I get 0.048. Now, I'm just going to convert decimals into percentages because to me, it just is easier to see what's going on. So the 95% confidence interval is that the difference between these two could be a negative 14.8, or it could be as high as a positive 4.8. So if you visualize what that might look like, there's 0. Over here is roughly 4.8, and way down here is negative 14.8. And anywhere at all in that interval is going to be the difference between the two. So that would typically be the end of the question as far as calculating a confidence interval is concerned. So now we're going to add another type of question once that's done. And that's, how do you interpret this? Well, in this case, the conclusion should be that there's not enough evidence to prove that one of these drugs is better or worse than the other. Now you might say, well, how do I make that assumption? Do you notice the number of zeros in this interval? Right? My finger pointing at it, right? If the answer could be 4.8, do you know that's saying that this drug is 4.8% better than that one? And at the other end, it's negative 14.8, which is another way of saying this guy is 14.8 smaller than that guy. So can you see that at this side, drug 2 is better, but at this side, drug 1 is better? There is no conclusive evidence that either one of those is guaranteed, right, to win. So what would an interval look like if there was evidence? Can you imagine we got an interval that looked like this? Negative 5% to negative 2%. Everybody is negative. Now, if every single, the difference between them is negative, right? If all of them are negative, doesn't that mean that when you take the first one and you subtract the second one, it's always, this is always smaller than that. That's why you get negatives. And if this is almost smaller than that, isn't that this guy's bigger than that guy? New drug better than old drug. And 3% up to 7%. Right? So in this way, this one is saying 2 is best. And what's this one saying? It's saying 1 is best. So can you see, if you look at the difference, you can compare 2 drugs, 2 tests, to anything. And by subtracting them, if the answer is always positive, it means the first one's bigger than the second. And if the answer is always negative, right, the interval contains nothing but negatives, right, then it means the second one is bigger than the first. And that's just math, isn't it? If you subtract 2 numbers and the answer is positive, doesn't that mean the first number is bigger than the second? We're talking about positive numbers here, right? And if you switch it around, it's the other way. So let's show you that same calculation, but using the calculator. So I kind of promised you a shortcut. So some of this information you won't be able to see because it's on the paper, but you'll trust me that it's here. So there's our calculator. Hopefully you're all seeing that, are we? Right. Now, there's a set of buttons to press. So if you just go back and look at this video, you can see what they are. Let's just start again here. I just want to have this thing at the bottom clear so you can just see the keys that I'm pressing right now. So you hit the start button. Done. You're then going to move over to the tests on the right hand side. And the guy that we want is hidden down here. So it's not in a very easy place to find. So I'm scrolling down. And a lot of people think you only get what you see, but if you keep hitting downwards, you see there's more stuff. Tons of stuff. We're going to go to number choice B. It's very cryptic, but what it's saying is 2 proportions Z intervals. Z, you know, my 0.95 guy. I guess they put it in there for that. So that's the guy that's going to get me my 90, 95, 99% confidence interval. So when I hit that, it asks me a lot of questions. So X1, how many people were in the first test that we got better? 150. How many were in the first sample? 200. You see I'm typing in the numbers. Second sample, there was 80 people got better. Out of 100 who were in that group. Now you see how it says level, 0.95, that'll get you a 95%. If I wanted 99, I just type in 0.99. If I want 90, I type in 0.90. Do you see, it's pretty much, you just tell it the numbers it needs and it'll do the rest for you. Pretty cool?
Yeah.
So that one's good. Go down to calculate, hit enter. Oh, for free, it tells you some stuff that you might have known anyway. There's P1 hat, there's P2 hat, there's the sample size N1, there's the sample size N2, but can you see our guys? They're a little bit more accurate. I think they're doing it to 4 decimal places. When you do the homework, it's so easy. I've done it myself. If they say to 3 decimal places, will you remember to write 3? Because I think if you write 4, it's probably just going to say error on you or tell you you're wrong when you truly weren't. Do you like the calculator taking the strain of the number crunching out of your hands?
Yeah.
Of course.
Okay. Well, not everybody does, because then they have, I can't remember what number goes where, and I can't remember where to find it, and you know, all those kind of questions. But if you know where it is, because it is kind of hidden, and you know what they're asking for, then really all they're doing is saving you hitting a lot of buttons, aren't they? They're just saving you hitting a lot of buttons, because the formulas were there. You could type them in and do what I did the first way. Here we go. Okay, so what I'm going to do is just do another example. And stop here. And I'm going to try, if I can, pick one straight out the homework. That way we kind of get used to the way the homework asks that question. So, it's a bit small. I don't want to muck about with my thing, because if I zoom in, I'll probably never zoom back the right way again. It says a research centre reports on a survey taken in which they asked whether responders have heard the good news about job markets. So evidently that was before things happened. They compared those making 30,000, so that's my first group, to those who made more than that, right? The 31 to 74,000 group. And what they're doing is they're looking at do they share the same opinion? Oh yeah, I've heard about how good the economy is, or I don't know what you're talking about, right? We're being looking at a 90% confidence interval for the difference in proportions. And they're telling us in this question what the answer is. So the answer is, I'll put it in big writing. Somebody has done all the working for us, at least in the early questions they do that. Now, if you like, that's -3% to +5%. And me personally, I think of where is 0? There we go. So we're being asked to type integers or decimals. Do not round, use ascending order, right? So you're basically just filling in gaps here. So this bit here, you're going to put in between -0.03 and +0.04. That's not really worth talking about. What's this? The percentage alone you've heard about the job market compared to. Okay, they're talking about different choices about what a 90% confidence interval says. If I look at this interval and I know it's a 90% confidence interval, I am 90% confident that the true difference between the proportions is somewhere in this range, right? That's all it basically tells me. And in this case here, is there evidence to show that the groups are different in any way? Well, the answer is, where is 0? If 0 is in your interval, it means there's no evidence that the two groups are different, because it could be this is bigger, this is less, it could be this is less, this is bigger, right? There's no way of telling. Now, if the entire interval is positive, right, 5% to 7%, right, always positive, right? In that case, there's evidence to prove that the first group is bigger than the second, right? So when your interval has nothing but positive numbers in it, it means the first group is bigger than the second. If your interval has nothing but negative numbers in it, then you've got evidence that the first group is smaller than the second. So you can actually tell if there's a significant difference between two groups by simply just calculating this interval. And if 0 is in the interval, you can't really tell. There's no significant difference, right? The two groups are pretty much the same. So let's see if we can jump to a question that's got some numbers in it. Okay. Here is some data. They've actually collected real data on this, but in this particular case, I think it's just put together for the question. They looked at children and they split them into two groups. Preschool and no preschool. And then they followed them and they found out if they graduated or they didn't graduate. And this is what that data looked like. 16 of them goes there, 15 of them goes there, 24 goes there, and 15 goes there. So the information that we want is in there, right? We just have to figure out which numbers are relevant to our story, right? So I'm going to call group 1 those who went to preschool, right? So when they were kids, they went to preschool. And then 60 of them graduated, right, and 24 didn't. And then you're looking at the ones that had no preschool. And let's see what happens. Right. Let's look at sample size. Right, we need to collect all these kind of numbers, so we need to know N1. When you're looking at the preschool, isn't N1 the 40 of them, right? So that's 40. And N2 is 30. Agree on that? Now, we're going to do a P1 hat, which is basically success. I would assume success here is you graduated. So P1 would be 16 out of 40. Which is what? 40% of that group graduated. Does that seem reasonable? Right. So P2 would be 15 out of 30. An interesting set of data. You would have expected, I would have expected anyway, wouldn't you expect these numbers to be flipped the other way around? If your kid went to preschool, you know, you'd expect they'll get a little help, you know, they'd probably graduate. But it looks anyway, based on this evidence at least, that the opposite of that is true, isn't it? That the ones who didn't go to preschool graduated at a higher rate than those who did. Well, there's a caveat to this in the big picture. This data isn't from just, 70, which is tiny, right? From 70 students. This data is a subgroup of people like inner city kids who've got a whole load of other issues in their life, right? Especially as they get older. And all you're seeing a reflection of here is that, you know, the area that you live in can have a very detrimental effect to your graduation. So even although you may have went to preschool or not went to preschool, it's not a strong enough factor to influence your graduation at high school, right? Me personally, do you know, making this off the top of my head, see if I wanted people in inner schools to graduate high school, do you know I would pay them money to go to high school? And I'd pay them money for turning up each day. And I'd pay them like it was a job. Your job is to go to high school and you get a big bonus if you pass. What do you think?
Sounds good to me.
Motivation is one of the biggest problems. And environment certainly makes it hard, but I mean, money is a very strong influencer in all sorts of behavior, right? So that's just me getting it over my chest. Now we're going to put this fella together, right? And we're going to get a, did they mention it somewhere? A 95% confidence interval. Now I could do this guy by hand, but I think the majority of you are thinking, this looks like it should be done on the calculator because it's going to be so much quicker, right? So I am going to bow to that idea. So we'll clear this fella out of the way. Gives us a chance to see the buttons again. So, can anybody just remember, I know we only done it once, but what was the button, where's define hidden? What's the first button to press?
That.
You got it. Now, where do I go next?
Go to test.
Now it gets a bit harder.
B.
Yeah.
Oh, God, that is very good. I don't think I would have remembered that.
Oh,
Just hearing it
I have a
once.
question.
Yes.
So if B is for 2 to
Yes.
figure out 2 of them, would A be to figure out 1?
Yes.
Yes.
Got you.
So I'll hit it. According to our sample, X1 was 16 of them out of 40.
Mm-hmm.
And then X2 was 15 out of 30. And it is a 95, so I can leave that alone, calculate, go. And the answer we get this time is negative 0.3347 to positive 0.13465, which is overkill. Let's pretend it was 2 decimal places this time. You'll see what I'm writing in a few seconds. So, we're going to look at this interval and see if anything we can conclude about it. Is there evidence to show that preschool, no preschool, had any effect on the graduation rate? Well, look at the interval. Isn't 0 in there? Isn't 0 between these two numbers, right? So I can tell you right now that there isn't enough evidence to say one is better than the other. It probably is. I can't see preschool hurting a child, right? I don't think getting more education ever hurts you, right? So, but I think it's just, the interval is huge. I mean, look at it, negative 33% all the way up to plus 13, right? Could be a huge difference either side. And 0's in the middle of that, so no good at all. No evidence. So for the last one, we are going to do a question where I'm going to make it so there's evidence, right? Just to show you that you can get some stories that work, right? So here is our third and final story. We're going to have a group here, and we're going to say males, we're going to do females. And we conducted a survey on do you like watching sci-fi movies, right? And I'm making this data totally up. And in this story, I'm going to give you the information, slightly wonky, so you'll see what I mean. 70% of the males said they like watching sci-fi, and that was out of a sample of 200. And 40% of the females said that they liked science fiction, and that was out of a sample of 400. Now, what's wonky about this is, do you notice that we know N1 and N2? And we actually know P1 hat and P2 hat. But if I'm going to use my calculator, don't I need to know what they call X1 and X2, which is how many people said out of that 200, I like sci-fi movies, and how many out of that 400 women said, I like sci-fi movies. So we have got to get that number, right, to go into the calculator. So how am I going to find out what it is based on what's in front of you?
0.7 times.
Right. 70% of 200, which if you turn it into decimal, it's 0.7 times 200, which is 140 people. And then the same thing is going to be over here, isn't it? 40% of the women like sci-fi, 40% of 400, maybe I should write that down. 40% of 400, which on a calculator is the same as that. Now, if you were looking at this information without really focusing too much on it, it looks superficially like more women watch sci-fi than men, doesn't it? There are 160 of them, right? And there are only 140. But that's really not a very accurate understanding of what's going on. Isn't there a lot more women in the sample than there is men? And so that has to be taken into account, right? If the samples are different sizes, the number of people who live with the new drug, or the number of people who like sci-fi, that's just naturally going to be bigger than that because there are twice as many people, right? Even if there was no significant difference. So what I'm going to do now, I am going to go and do a couple of them, but I'm going to do a 90% confidence interval first, and we'll see how that works. So 90, oh, I thought I'd done that. There we go. Since we're all good at remembering where things are, I'm just going to zoom really quickly to B. Right, the first group was 140 guys liked watching sci-fi out of the 200 that they asked. In the women's group, it was 160 of them liked to watch it out of the 400 that they asked. I'm going to change this to 0.90, so that's a 90% confidence interval, and then calculate. And the answer that I get here is 0.233 to 0.367. We got that, guy? Right. I'm going to come back to that calculator in a second, but right now just let's look at what we can see in front of us. Do you notice that every single one of those percentages is positive? So does it not make the male bigger than the female? Right, big, take away smaller, that's why it's positive, right? So conclusion, there's evidence that males watch sci-fi more than women. And that's when you get those little TV or internet articles. Do you know how they sometimes, you know, MSN, wherever it is you go looking, hey, they've just done a new survey and they found out it's statistically significant, right? In other words, you're pretty sure it's true, right? In fact, if you look at this interval, isn't that 23 to 36? See that? So not only can I say with a high degree of confidence based on this data that males like watching sci-fi more than females, can I also say that it's probably in the region of 23% more, right? The difference between them is at least 23, right? It could be as much as that, but we'll say at least 23. So not only can you say one's bigger than the other, do you see as an added bonus, you can even put a number on how much bigger than the other? At least 23% more. Now I'm going to do a 95% confidence interval. Do you think this interval is going to get bigger? In other words, you know, like 0.1 to 0.4 kind of thing. Or do you think this interval is going to shrink down? If you want to be 95% confident, what tends to happen to the interval?
Shrinks.
Well, let's think of it this way. I don't know what you can see. Yeah, right. If between here and here, I'm 90% sure. If I want to be 95% sure, don't I have to make it a little bit bigger just to be more sure? Right? And if I want to be 99, I make it even bigger. So we're going to do a 95, and then lastly, I'm going to do a 99. And then we'll return and we'll see what those intervals look like and see if my prediction that this one will be a bigger interval, right? It will start at a smaller number and finish at a bigger, right? And so on and so forth. So let's see if that happens. One of the nice things is that most of what I need is already there. So when I go start and I go over to test and I go down to the guy at the bottom, B, you see I've still got the data from last time. So all I need to do is hit a whole load of enters and change this to 0.95 and boom. Calculate. And this time, the interval is 0.22 to 0.38. And then I'm going in one last time, and I'm going to do a 99% one. And this time I get 0.20, 0.4, roughly. So to kind of finish today, let's see if this kind of makes sense. Right, we got our 90% confidence interval, and that is definitely evidence that males will like watching that sci-fi more than women, right? Even on a bad day, it's still a good positive difference, right? If you move it up to 95%, do you see how this number is a little bit smaller and this number here is a little bit bigger? The interval's grown a little bit. Right, if you go to 99, do you see it's growing a little bit more? This one here is, out of the three of them, this one here is one I like the most. Because what this is saying is that I am 99% confident that the real difference is somewhere in that range. Right, 99% is not perfect, guaranteed, but it's really strong, isn't it? And would you agree that even in that situation, I can also add with roughly 20% more men watch sci-fi than women? Now, all of this is based on an assumption. This data wasn't real. I never went out and collected it, right? But if this data was correct, right, if it was real data from real people, those conclusions would be totally valid. So in the medical field, when they say it's statistical evidence to show that new drug is better than old drug, it's very often this process here that they have used. There's another version of this process called hypothesis testing, which is what the next chapter is about, where we kind of formalize this process a little bit. But that's essentially what you do. You look at the difference between the two and you decide, is there evidence there to prove something? And in this case, I think there's strong evidence that there is. And just to finish, there is a rule called Murphy's Law. You know that one? You know, and if it can go wrong, it will go wrong. Even this one has a 1% chance of being totally wrong, doesn't it? A 99% confidence interval only means you're 99% sure that the real answer is somewhere in this interval. But you're not 100% sure. Couldn't the real answer be a way over at -10% or up as 82%? And so when you do something in statistics, and even if you do a 99% level, 1 in 100 times, you're going to screw up. And people are going to say, but you said this was evidence and statistical and all that other stuff, but you were wrong. And the answer is, yeah, you're right, I was wrong. 99% of the time I'm going to be right, but 1% of the time I'm going to be wrong. Now, when the thing you're talking about is guys liking sci-fi movies, I don't think it's the end of the world if I got it wrong. But if it's a new drug treatment, getting it wrong is not good, right? Because I could do one of two things, both of bad things. Can you imagine there's a new drug out that is actually better than the old drug, but the numbers didn't agree with that? Right? It's a 1 in 100 times it just didn't work. Couldn't that be a new drug doesn't go on the market because it isn't better than the old drug, right? Nobody's going to give you a new drug if it doesn't do a better job than the old drug, right? Because the new drugs are cost a fortune and, you know, not generic. Right? That's one. The second one is just as bad. Can you imagine that you got a 1 in 100 and you got it wrong, and you thought the new drug was actually better than the old drug? That's bad as well, right? Not getting a good drug is not good, right? But thinking you've got a good drug and it's not that good is equally bad. So that's us. Any questions for today?